Welcome, everyone, to our lecture on the comparative anatomy of vertebrates. Today, we are diving into one of the most incredible evolutionary adaptations in the animal kingdom, the avian air sacs. If you have ever wondered how birds can fly for thousands of miles or soar over the highest mountains without running out of breath, you are in the right place. We're going to build our understanding of this biological marvel from the ground up. To truly appreciate how special a bird's respiratory system is, let us first think about our own. Mammalian lungs work a lot like a simple hand fan. You push air in, and then you pull it back out through the exact same dead-end path. This means fresh air is constantly mixing with leftover stale air, which is not very efficient. Now, imagine a blacksmith's bellows that constantly pushes a steady, one-way stream of air into a fire to keep it roaring. Birds have evolved a brilliant system of internal balloons called air sacs that act exactly like these bellows, keeping a continuous flow of fresh air moving over their lungs. Now that we understand the basic bellows analogy, let us look at the formal anatomy. In comparative anatomy, air sacs are defined as thin-walled, balloon-like extensions that connect directly to the lungs. They can even extend into the hollow bones of the bird. It is crucial to understand that, unlike the lungs themselves, these sacs are not highly vascularized. This means they lack the blood vessels needed to actually exchange oxygen and carbon dioxide. Instead, they act purely as aerodynamic pumps and temporary storage reservoirs. By expanding and contracting, they force air to move through the bird's rigid tube-like lungs, which are called parabronchi. Building on that anatomical definition, let us see how these pumps actually coordinate. The air sacs are divided into two main functional groups. First, we have the posterior air sacs, which sit toward the back of the bird. These receive fresh air directly from the outside environment. Second, we have the anterior air sacs, toward the front, which receive the stale air that has just finished passing through the lungs. Driven by the bird's chest muscles, these two groups expand and contract in a highly coordinated rhythm. This guarantees that air moves in a single, unidirectional path through the lungs, providing fresh oxygen during both inhalation and exhalation. Let us visualize this incredible unidirectional flow with a diagram. Here, you are looking at a schematic of the avian respiratory system. Notice the trachea at the top where air enters. The blue arrows represent fresh air. You can see it bypassing the lungs initially to fill the posterior air sacs at the bottom. From there, the fresh air is pushed across the central lungs, labeled here as parabronchi, where gas exchange happens. The red arrows show the now stale air moving into the anterior air sacs before being expelled back out the trachea. This visual perfectly illustrates how the lungs are constantly bathed in fresh air, never mixing with the stale air. Having seen how the system works visually, we must ask, why did this evolve? The answer begins with the extreme metabolic demand of flying. Sustained flight is one of the most energy-intensive activities in the animal kingdom. It requires massive, uninterrupted amounts of oxygen just to keep the flight muscles firing continuously. If birds had a standard mammalian respiratory system where fresh and stale air constantly mix, they simply could not extract enough oxygen to stay aloft. The evolution of the air sac system represents one of the most significant leaps in vertebrate anatomy, solving this massive biological problem by maximizing oxygen delivery. Beyond just basic flight, This system is pushed to its absolute limits during migration. Many birds, such as the bar-headed goose, migrate at extreme altitudes, flying directly over the Himalayas. At these incredible heights, the oxygen concentration in the air is dangerously thin. If a mammal tried to perform intense physical labor in this environment, it would literally suffocate and fail. However, the avian air sac system guarantees that the gas exchange surfaces of the lungs are constantly bathed in 100% fresh, oxygen-rich air. This maximizes extraction efficiency and makes survival in these extreme low-oxygen environments entirely possible. To truly appreciate the advantage of air sacs, we can look at the mathematical model of respiratory efficiency. In physiology, the actual amount of fresh air that reaches the gas exchange surfaces per minute is called the effective ventilation. The formula for this is VF equals F times the quantity VT minus VD. Let us break down these symbols. VF is the effective ventilation in milliliters per minute. The variable F stands for respiratory frequency, or breaths per minute. VT is the tidal volume, which is the total air inhaled in a single breath. Finally, VD is the anatomical dead space, the volume of air trapped in the windpipe where no gas exchange happens. Because birds have massive air sacs, their tidal volume, VT, is drastically larger, which mathematically minimizes the penalty of the dead space. Now that we have our formula, let us see this with a concrete numerical example. Imagine a small mammal and a bird of the exact same body weight. Both breathe at a frequency of 30 breaths per minute, and both have an anatomical dead space of 5 milliliters. However, because the mammal only has lungs, its tidal volume is just 15 milliliters. We want to calculate the effective ventilation. For the mammal, we substitute 30 for F, 15 for VT, and 5 for VD. Subtracting the dead space leaves us with 10 milliliters of useful air per breath. Multiplying this by 30 breaths per minute gives the mammal an effective ventilation of 300 milliliters per minute. This is our baseline. Continuing with our comparison, let us look at the bird. Thanks to its expansive air sacs, the bird can take in a much larger breath, giving it a tidal volume of 45 milliliters. We use the exact same formula. We substitute 30 for F, 45 for VT, and 5 for VD. Subtracting the dead space still leaves a massive 40 milliliters of useful air per breath. Multiplying 40 by 30 breaths per minute gives the bird an effective ventilation of 1,200 milliliters per minute. Physically, this final answer shows that simply by having air sacs to increase tidal volume, the bird receives 4 times as much usable oxygen per minute as the mammal, perfectly explaining their immense energy generation. Let us apply this to a real-world survival scenario. A migrating goose is flying at an altitude where the air is very thin. To keep its flight muscles working, it requires a strict effective ventilation of 4,000 milliliters per minute. The goose has an anatomical dead space of 20 milliliters and a massive tidal volume of 120 milliliters. We need to find out how fast the goose must breathe, meaning we solve for the respiratory frequency, F. We substitute our known values into the equation. Subtracting the dead space tells us every breath delivers 100 milliliters of fresh air. Dividing 4,000 by 100 gives us a final answer of 40 breaths per minute. This is a very manageable breathing rate, making high-altitude survival mathematically possible. We have covered a lot of ground today, so let us summarize our key takeaways. First, remember that air sacs are the ultimate biological bellows of the vertebrate world. While they do not absorb oxygen themselves, their ability to store and pump air ensures the bird's lungs receive a continuous, one-way flow of fresh oxygen. This anatomical masterpiece completely overcomes the limitations of the mammalian two-way system. By drastically increasing tidal volume, birds maximize their effective ventilation. Ultimately, it is these delicate, invisible balloons that conquer the thin air of high altitudes and make the miracle of sustained flight a reality. Great job following along with both the anatomy and the mathematics today.